Okay, good morning once again to all of you. Uh, Welcome to this fourth day of GIN course. Now, sir will be continuing with magnetic recording with what he has left yesterday. So today he'll have two lectures, right, of 3 hours. After lunch, we will have a discussion or maybe tutorial that we will see. So,
2 or more lecture.
Huh?
2 or more.
Yeah,
Until I finish, I won't leave you.
Okay, we'll be finishing the contents. Yeah. So post lunch we will have a discussion and maybe tutorial. But before lunch, yes, two lectures, as it is mentioned in the schedule. I hope you were there in CIR. Any feedback that you wish to let us know? You did some experiment? No. No. Did you send the sample? Give this? Could you give the sample to them? No. What had happened? Now today? Okay. So now I request Pastor Prem to continue.
Okay, thank you. Yeah, good morning. So I hope you all have joined OCLAB. So currently in my lab, right, I have 6 Indian students, and the first lesson I teach all of them is to be punctual. Inevitably, all of them come late. So the first lesson I teach them is the punctuality. So when I have meeting, I go on time or maybe 5 minutes before the meeting. So please be punctual. So this is one of the bad qualities, not quality, whatsoever we have. Okay. Yes.
What sir has said earlier, I have been part of some meetings where President of India used to schedule a meeting. Pranab Mukherjee. So I tell you, he was so particular about timing. President of India, if he has scheduled a meeting at 10 a.m., the moment your clock clicks at 10, he is in.
Mm-hmm.
And that if the meeting is of 1 hour, he'll be there precisely for 1 hour. The moment 1 hour is over, he's out. So you see, if you are going to attend any professional thing, please be punctual. Sir has rightly said it's not a good thing that we are. It's not a good message that we are taking.
Yeah. Also, I don't like students waiting outside my office. So I give them time. Then they should. Yeah.
Basically, I think Indians have this kind of mentality. We have the director. I was sharing it with sir. Director of the institute being so occupied, but he is so particular, so punctual about the timing. He has said 9:15, he is there. Yesterday also I just sent a message that the program will start at 9:15. I was out waiting outside. Immediately at 9:15 it came. So he is just following that program. So please be and try to maintain KTU. I'm sorry, sir, but
No, 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 not your problem. Okay, so today I titled this as day 4A because I don't know, maybe we will have BC, we don't know. So today we will cover magnetic recording progress and obstacles. And before that, about yesterday's tutorial, I think you would have done some questions. How many of you did plot the Excel file? I gave you some questions where you are supposed to plot the M versus H curve, right? How many of you plotted? Okay, the idea of those questions are like this. So you learn by many ways, right? By looking at things, by listening, by reading book. Okay, there are many ways to learn, and there's also another way to learn is by doing. Okay, so you go do experiment, then you learn, right? So in this case, I wanted to let you know how the M versus H curves of different materials look like. So if you plot, right, you will really have some understanding. If I try to draw the image curve, not just me, anyone, right, when they draw, they will always miss some point, but you really plot the real data, then you will have the perfect idea. So if you haven't done yesterday, you go and do later. Okay, so yesterday we learnt about the basics of magnetic recording. So I gave you some idea of in plane or longitudinal magnetic recording, and I taught you how we can read information, how we can store information, and how we can write information. Especially from the recording media point of view, I discuss that the signal to noise ratio at high densities is what matters more. So today we will continue on that aspect. Okay. So we learnt that if we have to write information on the disk media, we have some limitation on the writing heads. So writing head cannot produce more than 1.5 Tesla, something like that. You know the best known, okay, maybe I ask you. So what is the best known material in the world with the highest saturation magnetization? Iron cobalt. Okay, so iron cobalt with what is the composition? Somewhere like 65-35. Okay, so you take iron and dope, not dope, replace 35 atomic percentage of iron with cobalt, then you have the highest saturation magnetization. So that material has a saturation magnetization of 2.4 Tesla. So the maximum field that you can produce without spending more energy is 2.4 Tesla. Okay. And when you create recording heads because of the spacing and all those things, you will be able to achieve 1.5 Tesla or so. So you have a write field of 1.5 Tesla, and if your saturation field is more than 1.5 Tesla, you cannot write information. So we need to have suitable saturation field, and for storing information, we need to have suitable coercivity, nucleation field, and so on. And when we talk about reading information, we should have sufficient signal, low noise, and optimized MRT. So I told you that MRT is related to signal. So if you increase MRT, you will find that the signal increases, but beyond certain point, if you increase MRT, the pulse width, the width of the pulse will become larger. So that's like having a pen with a large tip. Okay, you don't want a pen with large tip, right? So we don't want to increase the pulse width too much. So we don't want to increase MRT beyond certain point. So all these are need to be taken care of. So yesterday we learned that we want to reduce the noise. So we have to reduce the DC erase noise. So to have the lowest DC erase noise, we have to maximize the number of in plane. Suppose you are doing longitudinal magnetic recording, you have to maximize the in plane magnetization. Okay, so you don't want any tilt out of plane. Okay, so this is something that we need to take care. And when you do perpendicular recording, you want the magnetization to be completely pointed perpendicular, not having any tilt. That will help to reduce the DC erase noise. And if you notice here and here, you notice that the magnetization within the plane is random. Okay, so within a circular or cylindrical domain, the magnetization in plane can be in any direction, 360-degree possible. But if you maximize this magnetization along one particular direction, that also will reduce the DC erase noise. Okay, secondly, we learnt that the grains must be well isolated, only then they will reverse independent of each other. So, I showed you the funny video where guys are sitting on a wall and they all fall down because there is a coupling, right. So, in magnetic recording media, you want to break the exchange coupling between the grains. So, you have to isolate each of them. So, there should be some spacing between the grains that will help to reduce the transition noise. So, I taught you the compositional segregation yesterday, which means you have certain composition within the grain. So, grain is magnetic and you have another composition at the grain boundary. So, grain boundary is non-magnetic. So, this way you can isolate the grains from each other. Isolate means it may be physical isolation or it may be magnetic isolation. Okay. So, you can have a non-magnetic material and break the exchange coupling. So, the spins of this cannot be coupled to the spins of the neighboring atoms. So, that is what we do. So, we want to reduce the transition noise, we must isolate the grain from each other, and we also want to make the grains as small as possible. So, if the grains are bigger, you try to write a bit somewhere here, then it has to go through a very large region. The transition cannot happen through half of the grain. So, it has to go through the grain boundary. So, if there are big grains, you will have very big transition. If you have small grains, you will have smaller transition. So, grains also must be as small as possible. So, these are a few things that we learned yesterday. So, typically how people try to minimize the magnetization from pointing away from the plane. So, we do not want this kind of out of plane magnetization for in plane magnetic recording. So, we want to make them as parallel as possible. So, to achieve that, people will use some underlayer. So, just a magnetic layer is not enough. You want to force the magnetization to be parallel to the substrate. So, people will use some underlayers like chromium. Okay. So, if you take some substrates like aluminum, magnesium, and you deposit chromium at a temperature of around 250 degrees Celsius, then you can grow most of the chromium grains to have this 200 plane parallel to the substrate. So, if you do XRD, you will see some peaks like this. So, you see chrome 200 is parallel to the substrate, and the chrome 200 has a lattice matching to cobalt 110. Okay. So, now after depositing chromium 200, if you deposit cobalt 110, so this atom will be matched to this atom will be matched to this atom, and so on. Okay. So, it is like Lego blocks, right. So, you have two Lego blocks of same size, you can plug one Lego block on the other block, right. So, in a similar sense, we play Lego with the atoms. So, once you grow chromium with a 200 texture, we can grow cobalt 110 plane. Okay. So, where is the EZ axis here? Where is the EZ axis of magnetization in this picture? It is along the C axis, which is along this direction. Okay. So, this way we make the magnetization horizontal to the disk surface. So, you see, once you deposit some chromium around 6.3 nanometer, you see a larger cobalt 110 peaks, which means many of the cobalt grains are oriented parallel to the disk surface. So, this is one way to explain why we just do not use one layer for magnetic recording. So, we need some layers to keep the magnetization in plane and so on. Okay, so now we slightly move. So all these stories that I have told you now is until 2000. Okay, now we look at the period of 2000 and so on. Okay, so if you look at the history of the hard disk drive, so Professor Naresh told you that the first ever hard disk drive had a capacity of 5 megabyte. Okay, you don't know how, I don't know, some of you may not know how it looked like. So this is the hard disk drive. Okay, this whole, this cupboard kind of thing. Okay, so this is the one that store 5 megabyte. So you see that there is a cylinder, right? This cylinder is actually 24 disk placed one top of another. So there are 24 disks of 2 feet diameter. So this is what stored 5 megabyte of hard disk drive, and it has to be lifted into the airplane like this. Okay. Whereas now you can buy a 5 terabyte hard disk drive, which is 1,000,000 times larger, and you can put it in your pocket and walk around. So this is the kind of growth that we have seen over the last 70 years. Okay. So I prepared this slide, this particular slide maybe like 25 years ago. At that time, Petronas Towers was the tallest building in the world. Okay. So I use this as an example. So now you have a hard disk drive with 5 terabit per square inch capacity, 5 terabit. Okay, it's not terabit per square inch, it's terabyte, maybe 1 or 2 terabit per square inch. So if you look at that product, the bit length is like 10 nanometer or 12 nanometer. Okay. So this bit length of 10 or 12 nanometer is like shrinking the Petronas tower to the height of an inch. Okay. So if the bit length of the first ever hard disk drive was as tall as this tower, now the bit length is only this small. Okay. So imagine miniaturizing the whole Petronas tower to the size of this. Okay. So that's what we have done. So that much shrinking has happened in the bit length. So similar case is the track width. So if the tracks are as wide as the height of the Petronas tower, now again the track width is like 1 inch, this length. So we have miniaturized the whole Petronas tower to this length. So that is the miniaturization the hard disk industry has done. So because of that, the amount of information that store in a given area has kept increasing. So we have gone from 1 e minus 6 all the way to 1000. Yeah, 1 terabit per square inch we have already crossed. Okay. So again, you can see we have grown a billion fold in terms of the aerial density, and the price keeps falling. Okay. So this was plotted long ago, but if you look now, it may be even further beyond the graph. Okay. So this gives you a trend of how the aerial density has increased, how the price keeps falling, price per gigabyte, okay, not price of the hard disk drive. Price of the hard disk drive is more or less same, always $100 US somewhere there, but the price per gigabyte will keep dropping. So this kind of growth has happened because of two reasons. Okay. The first reason or first way, two ways, okay, two methods have helped to achieve this kind of growth. So the first method is called scaling. Okay. The second is major technological innovations. Okay. So this is another graph looking at the price of the hard disk drive. I told you the price of the hard disk drive is always around $100, right? So that's somewhere here, but in the past it used to be more. Okay. So here you see a steep drop in price. This happened because of the magnetoresistance sensor. Okay. Before the magnetoresistance sensors, if you want to make a certain capacity, you need to stack many disks. With many disks, many read sensors, you will have high capacity. but once the magnetoresistance sensors came into picture, then the sensitivity was increased, then people could double the density every year. So, from 99 to 2001, people could double the capacity every year. Then they need less disk, fewer head, so the price dropped. After that, it almost settled to the same price of around $80. Okay, so here you see a sudden spike. Okay, any guess? Okay, if you look at the price of DRAM now and the price of DRAM 2 years ago, what difference do you see? Prices increased, right? Normally, you would expect that the semiconductor technology, the price should go down. That has always been the trend for 20-25 years, but suddenly in the last 2 years, there has been a drastic increase in the price of the DRAM, because the demand exceeds the production. So, I told you that all the manufacturing plants have certain production capacity, and if the demand exceeds the production, then the price will go. So, in this case, what happened, the demand was always there, but production did not happen much because of the flood in Thailand. Okay. There was in 2011 there was a flood in Thailand, and Western Digital has a lot of factory, so they stopped producing. Okay. So, that is the reason why you see that the price increased. Anyway, except for those minor glitches, you will notice that the price is always the same. Now, again the price is increasing because now the growth of the areal density is not that high. I told you at some point of time areal density doubled every year, but now the increase is like 5% or 10% in areal density. So, if you want to make high capacity drives, you have to increase the number of disks. Okay. So, we need to increase the number of disks. So, we are going back to this trend again. We came down, now we are going up again. We need to make more disks, more heads, and so on. Okay, so I told you that there are two ways in which we achieved the growth. So, first method is called scaling. Scaling means basically reducing or reducing or increasing something by certain factor. Okay. For example, let us say you are making 1 gigabit per square inch hard disk now. Okay. So, you want to move to 2 gigabit per square inch. Okay. Then what you need to do, you have to reduce this by to 70% of the current value and reduce the track width to 70% of the current value. Okay. So, if you make 30% reduction here, 30% reduction here, you will go from that technology to this one. Okay. So, is reducing something or increasing something. Okay. So, by scaling, you can go from one technology to other technology. So, this looks easy on paper. So, you just need to reduce the track weight, reduce the bit length and so on, then you can move on to the next level, but it needs a lot of research. So, to go from this technology to this technology, you need to reduce the grain size by 50% and things like that. So, similarly, if your the spacing between the head and the disc was 10 nanometer, next level you have to go to 9 nanometer, 8 nanometer and so on. So, you have to keep reducing something, or sometimes you may also have to increase something. Okay. So, that is scaling. So, it is not easy, but that is one approach to do. Okay. So, here I show you a magnetic force microscopic image of a hard disk drive. So, with a magnetic tip you can sense the magnetic flux and you can look how the image of the recorded bits look like. Okay, so, this was possible very long ago when the track width was wider and bit length was wider and so on. Okay, but now we have, in this picture the bit length was 200 nanometer, track width was 2.5 micrometer, So, MFM has a good resolution to meet this kind of images, but right now the bit length is 10 nanometer, track width is around 14 nanometer. So, MFM does not have the resolution to look at this kind of images. Okay. So, when you talk about scaling, you want to go from this level to this level, you have to make the grains smaller. Okay. For example, let us say you have certain grain size, if the grains are larger, I told you that the grain boundary and bit boundary are identical. So, the bit boundary has to happen through the grain boundary. So, if large grains, then the the pulse width will be large. Okay. So, you will have broad transition, but if you make the grains smaller, the transition will be narrower and so on. Okay. So, when you move from poorer technology to better technology, you have to keep reducing the diameter of the grains. Okay. So, this is one example of the growth or reduction in the grain size. Okay. For example, in 1999, when the areal density was 7 gigabit per square inch, the grains look like this. And when we move to 2002, and the areal density is like 35 gigabit per square inch, you can see the grains are much smaller, right? Compared to this, the grains are smaller. Okay. So, this again brings us back to the topic we discussed yesterday. So, yesterday I told you can achieve compositional segregation. So, you can have grain to be magnetic, grain boundary to be non-magnetic by choosing suitable dopant and suitable deposition condition. Okay. So, in this case the dopant material was tantalum, but in this case the dopant material was boron. Okay. So, when you use boron, the boron and some other elements diffused the grain boundary very well, much better than what we discussed yesterday. Okay. So, by choosing suitable dopant material, they could make the grain sizes smaller. Okay. So, this is one way to progress. So, keep reducing the grain diameter, then you can make the bits smaller. So, imagine you try to write one bit here, another bit here is possible. You can make this small bit, but when you go here, when the grains are bigger, the bit length will be very large. So, if you look historically, the grain diameter kept reducing as a function of time. So, this is the grain size. So, it kept reducing. So, if you compare the volume, right, again, so the grain volume has reduced so much that it is like shrinking the volume of Petronas towers to the size of a tennis ball, something like that. So, in recent products, if you take a square inch, okay, so we have like 15 trillion grains within 1 square inch. So, the grains are so small that we can pack 15 trillion grains in a square inch. So, that kind of growth has happened. So, reducing grain size is one way to increase the areal density. And yesterday we did not discuss this one, PW50. Basically, PW50 is the width of the pulse. So, you can imagine that to be the tip of the pen. Okay. So, you want smaller tip for writing more data, right. So, if PW50 is large, then you cannot pack information at close distances. So, we need to reduce the PW50, and PW50 is proportional to MRT. So, that is why I told you cannot increase the MRT too much. Okay. If you increase the product of remnant magnetization and thickness, you are going to increase PW50, which is not good. So, you want to reduce this, and PW50 is inversely proportional to coercivity. So, if coercivity is large, PW50 is small. So, we want to increase MRT, we want to decrease MRT, increase coercivity. Okay. So, if you look at this picture, the circle is coercivity. So, coercivity has been increasing. So, when you go from poorer density to better areal density, the coercivity kept increasing and the MRT was dropping, right. So, from say 1.2 millimu per centimeter square, the MRT is reduced to like 0.3, 0.4. So, typically people reduce the MRT by reducing the thickness. So, you want to make the film not too thick. So, basically this is reduction in the thickness of the films. Okay, so, as a summary, scaling means reducing or increasing some parameters. So, not only in the magnetic recording, in the case of semiconductor industry also people do scaling. So, they will scale the dielectric constant up, they will they will try to increase the dielectric constant and they reduce the transistor length and so on. Okay, the scaling helps to increase the hard disk drive areal density. So, basically people reduced grain diameter for many years. I showed you picture of the grain diameter kept reduced for many years, thickness is reduced continuously and the coercivity has been increased over several years. So, I told you the example of a credit card. Credit card was one of the magnetic recording technology in the past. So, you have 700 Oersted coercivity. Credit card or magnetic tapes with 700 Oersted coercivity. Now, we have moved to like 6,000, 7,000 Oersted kind of technology in hard disk drive. Again, if you take the credit card for example, the thickness of the film would be several micrometer, but now we are using few nanometer kind of films to store information. Okay, so thickness has been reduced, coercivity has been increased and so on. So, this is how the progress happened. So, let us do some question. Okay, first question. So, this should be Gyan day 4, not spin week 5. Okay, all of you are right, very good, happy to see that. Okay, so you learnt about DC, erase noise, transition noise. So, they are all related to recording media and this is the one that is not related to recording media. Okay, next question. Okay, scaling does not mean reducing everything or increasing everything. It is reducing some parameters like thickness, MRT you are reducing and increasing some parameters like coercivity is increased, grain size is reduced. So, 2 is the correct answer. Okay, so when you reduce grain size, you can increase SNR and you can reduce PW50. So all of the above is the correct answer. Okay, so we have touched upon scaling. So you understood what is scaling. Now let's go through major technological innovations. Okay, so before that I will tell you a story. Okay. So we all uh, think that we invented chess. Okay, Indians invented chess, but some other countries, I think they invented chess. Anyway, that's not our dispute. The story here is that the inventor of this is a Russian story. Okay, so let's time being imagine that it was invented in Russia. Okay, so the guy who invents chess, he goes to the king, and the king was very happy. So the king asked the guy, ask what you want, I will give you. Okay, then the guy who invented chess tells the king that I want a very simple request. I want 1 wheat grain for the first square, 2 for the second square, 4 for the third square, 8 for the fourth square, and so on. Okay. Then the king was okay, very simple. Okay, go, and then he orders his people to give him the wheat. Okay. Then after a few days, his people comes to the king and tell him that we don't have any more wheat to give to the guy who invented the chess, right? So you know how things go, right? One first square is 1, 2, 4, 8, 16, 32, 64, and so on. It will look simple in the beginning, but if you go all the way to 64, 2 power 64, right? 2 power 64 is a very large number. So it's 2 times 10 power 19 grains. That's equivalent to 1.2 times 10 power 15 kilogram of wheat, whereas the whole wheat production at this point of time is like 10 power 11 kilogram. Okay, at that point of time, imagine Russia alone cannot even produce this. Okay. So this is the problem of growth happening or doubling every year. So I told you at some point of time, the hard disk drive capacity was doubling. So at that point of time, it was easy, like we were somewhere here, or maybe even here, maybe doubling is easy. But once you are here, the doubling gets difficult and difficult. Okay. So you may have to go from 2 billion to 4 billion, and so on. Okay. So it's going to be difficult, and that kind of problem happen in semiconductor industry. It's also happening in the hard disk industry. Okay, so by scaling, what did we do? We kept reducing the thickness. So we went from a larger thickness to smaller thickness, and we reduced the grain sizes. So we make larger diameter to smaller diameter grains and so on. So if you look at the bits in a lower density hard disk drive and higher density hard disk drive, they will be shorter in height, okay, and smaller in diameter and so on. Okay, bit length is less compared to here, track width is less compared to here, and so on. Okay, so this is what we have been doing with the scaling, and this leads to a problem called thermal stability of magnetization. Okay, so we all imagine that if you magnetize certain hard magnetic material and leave it as such, the magnetization will be stable as a function of time, but that's not the case. Okay. So here I am just illustrating what happens in a cobalt cube. Okay, this is not a simulation, but it is just an illustration. Okay, some animation to show you what's happening. So here I have a cobalt cube of 30 nanometer dimension. So length is 30, height is 30, width is 30. Okay, so it's a cube of volume 30 times 30 times 30 nanometer cube. And here we have cube of 10 nanometer, 8.5 nanometer, 8 nanometer, and so on. And I saturate all these cobalt cubes to have magnetization pointing in this direction. Okay, now I look at the magnetization of these 4 cubes. So you can notice that the 30 nanometer is retaining the magnetization in this direction. 10 nanometer also no problem. But if you go look at the 8 nanometer one, it is rapidly fluctuating. Okay. 8.5 nanometer also is fluctuating, but not that rapid. So, it is going from left to right once in a while, not that rapid. So, what is happening here is that the magnetization is not stable. We are not doing anything, we are just keeping this at room temperature and we are just observing, there is no magnetic field. So, after we saturate the magnetization along this direction, we have removed the magnetic field, no magnetic field, we are just observing the magnetization, but the magnetization keeps fluctuating as a function of time. So, here is one sample that I measured. Okay, so, I keep a piece of recording medium in the VSM, I saturate with certain field, remove the magnetic field. So, no external magnetic field. I am observing the magnetization of the sample as a function of time. Okay, so, I notice that the magnetization keeps dropping as a function of time. We are not doing anything, we are just observing the magnetization and the magnetic moment of the sample just keeps dropping as a function of time. Okay. So, this happens because of the competition between two energies. Okay. So, I told you that there is an energy barrier KUV. KUV is responsible for storing or retaining the data. Volume, no, the volume, yeah, yeah. So, KUV is the energy that is responsible for storing or retaining of data. So, this is the magnetic anisotropy energy, but we also have another energy, right, thermal energy. So, at room temperature, for example, we have the thermal energy KBT, okay, Boltzmann constant multiplied by temperature in Kelvin at 300 Kelvin. So, we have sizable thermal energy. So, when the KUV becomes comparable to KBT, then we will see the effects of thermal energy. Okay. So, I told you in the old technologies, until late, I mean until 2000s, the volume was very big. Okay. You can say the thickness was, okay, let me give you some number. Okay, some number like this. Okay, so you have the grain diameter maybe more than 15 nanometer, height around 20 nanometer. So, when you have such large volume, you multiply by KU, you will have a very large number for KUV. So, that number is anyway very large compared to KBT, but when you shrink the grain diameter to say 8 nanometer or 9 nanometer and make the thickness to be 15 nanometer. So, there is a huge reduction in the volume. Okay. So, very similar to what I showed you here. See here you see between 8.5 and 8 itself there is so much difference, right. This does not fluctuate that rapidly, but the magnetization of this fluctuate very rapidly. Okay. So, two energies compete with each other. KUV tries to keep the magnetization the direction that you have set to be. KB2, the thermal energy tries to disrupt it. Okay. So, when there is a thermal energy, the magnetization will probabilistically attempt to change to another direction. Okay. So, these two energies compete with each other and this results in a time tau, okay, lifetime tau. So, this F naught is called the frequency of attempt. So, how frequently the magnetization tries to attempt to go to another direction. Okay, so, if this number is very large, tau is going to be large. So, if tau is large, then the magnetization will not if tau is large, this number will be small. So, the decrease will not be much. Okay. On the other hand, if this number is small, tau is going to be small. If tau is small, this number is going to be large. So, exponential decay will be large. Okay. So, that is what you are seeing here. So, here in this particular sample, the KUV by KBT, the ratio between is roughly 45 or something. Okay. So, the KUV by KBT determines how stable is the magnetization. The ratio between the magnetic anisotropy energy that retains the information versus the thermal energy determines the thermal stability. And if you make this number to be 60, okay, then the data will be stored for 10 years. Okay. So, you can use this formula, substitute 60 here, then find out how much magnetization will be decaying and so on. So, people have calculated that if this number is 60, then the data that you store in the hard disk drive will be kept intact for 45 is the one, this sample, that the one I measured. Okay. So, when KUV by KBT is 45, then this drops. Okay. This is not good, this is not desirable. So, here you see the magnetization is within 1000 seconds the magnetization drops so much. Okay. When this number is larger than 60, then the data will be stored for many years. So, for example, when you have the samples of 2000 or before, they have a very large volume. So, KUV by KBT is much larger than 60, but somewhere in 2000 we started having this problem. So, we entered a region where the KUV by KBT becomes comparable to 60. Okay, so that is one thing. Secondly, in your recording media, not all grains have the same diameter, right? So, there may be some small grains, some bigger grains. See these grains are smaller. Okay. So, they will have much lower KUV by KBT because their diameter is small and they will decay first. Okay. So, in a group of particles, some particle will switch their magnetization because they are smaller in size, their KUV is much smaller compared to KBT. As a result, you will always see some decay. So, in this graph, some decayed first, maybe these are grains with a smaller volume, then larger volume will stay for longer time, but eventually many of these grains will flip their magnetization. Okay. Okay, so this kind of property can lead to what we did not discuss on day 2, a property called super paramagnetism. Okay, so, you learnt that in paramagnetism the neighboring spins are not parallel. Okay, the neighboring spins have random magnetization and they fluctuate as a function of time. Okay, that is paramagnetism, right. So, what is super paramagnetism? So, super paramagnetism is a form of ferromagnetism, which means the neighboring spins are always parallel. Okay, the neighboring spins are always parallel, but as a collection. For example, let us say this is a small grain and I have another grain where again the spins are like this. So, when you have collection of spins like this, the magnetization is in this direction, right. So, in superparamagnetism what happens is that as a collection of spins, their magnetization flips between up and down. So, together they flip direction. Okay. So, the ferromagnetic property is still maintained, but as a collection the magnetization keeps fluctuating as a function of time. Okay. So, you can say that the superparamagnetism is an extreme case of low KUV by KBT. So, when I say how low, typically when you see that the KUV by KBT is below 20 or about 20, then all the magnetization will flip very rapidly. Very rapidly means in time scales smaller than seconds. So, it could be some milliseconds. So, every millisecond they will flip as a function of time. As a result, if you measure the magnetic property of the sample, there will be no coercivity. Okay. So, they will just show a loop shown by the red color here. The magnetization will just increase or decrease, but there will be no coercivity. Okay. So, the particle will have high Ms. Okay. Ms is not affected because the material is still ferromagnetic. It is not a paramagnetic material. The neighboring spins are parallel. So, if you apply high magnetic field, all the spins will point in the direction of your applied field. So, they will exhibit as high Ms as any other material. For example, I use the same material like let us say cobalt. Okay, this is cobalt with a larger diameter grains, cobalt with smaller diameter grains, cobalt with even much smaller two sample. Okay. So, this sample and this sample will show the same Ms, okay, but this particular sample will show coercivity in the hysteresis loop, this one will not show. Okay. Because the KUV by KBT is so small, the magnetization will keep fluctuating as a function of time. They do not retain the information. Okay. So, as they do not retain the information, that is why they have 0 MR. At high field, you can force all of them to point in one particular direction, but once you remove the field at room temperature, they will be at a random direction. So, the net magnetization will be 0 at 0 field. Okay. So, we can say that the paramagnetism is a result of competition between the exchange energy and KBT, Heisenberg exchange integral and KBT, but superparamagnetism is a result of competition between KUV and KBT. Okay. So, let us say a sample has a large KUV by KBT, you magnetize in certain direction and you observe the magnetic moment after some time T1, T2, T3 etc., it will be the same, it does not flip. On the other hand, if you have a superparamagnetic particle at time T1 it has certain magnetization, if you observe the same particle at time T2 the magnetization is different. Okay. So, they keep fluctuating as a function of time. So, this is superparamagnetism. So, here I prepared some table based on the KUV by KBT, how long it will take for the magnetization to reduce and so on. So, if you notice here when the KUV by KBT is very large, say above 100, the magnetization does not change much even after 10 years, okay, 60 also the same. But when you go below 60, here the magnetization has dropped by a few percentage, less than few percentage, but when you go for 40 for example, the drop is very large. Okay. So, we do not want to go into this region, we want to keep the KUV by KBT to be larger than 60. Okay, so if KV by KVT becomes smaller than 60, we will have data loss. Okay, the information you stored will be gone. You don't want that. And as I told you, the recording media will have grains of various diameters. So, there will always be some grains smaller than the average grain diameter. So, they will switch their magnetization. So, we want to minimize that. And in hard disk drive, this problem of KV by KVT appears because we reduce the grain diameter and we reduce the thickness of the films. Okay, so I show you this animation to show what happens. Let us say this is some particular technology where the grain diameter is so much and the bit length and bit sizes are so much, but as time progresses, we make the grain smaller, we make the bits smaller in length, tracks smaller in width and so on. So, as the grain diameter shrinks, if you do not do anything, you can see that some magnetization, some grains have switched, right. So, if you do not do anything, if you just keep reducing the bit length and track width, some grains will always flip the magnetization and you lose data. Okay. So, here you can see up domain down, here you can say 1 and 0, here you do not see anything, no difference. Okay. So, this is what will happen if you do scaling without taking some effort. Okay. So, let us do some questions. So, when I taught you the domain concept, I told you that beyond certain diameter or whatsoever, you will have multi domain, and below certain critical dimension, you will have like single domain, and the coercivity will decrease, something like this, right. So, that is because when you reduce the diameter, you are reducing the KV by KBT. Okay. So, maybe here the KV by KBT was 300, 400, but as you go smaller, you are going to smaller KV by KBT, and at some diameter you will reach the super paramagnetic limit. But once you exceed this, you are entering into the multi-domain region. That is totally a different concept. We are now focusing here. Okay, we are talking about the single domain region where Stoner-Woolforth type reversal happens. Okay, thermal stability refers to the stability of magnetization over longer periods of time. So, this is the correct answer. For any question, there is always two people who give wrong answer. Okay. Okay, next one. Okay, again 2. Okay, thermal stability depends on isotropy, it depends on volume. So, both must be clicked. Okay. Okay, next one. Okay, so this question is to test how well you listen. Okay, if your physics is solid, then you can answer. Otherwise, if you have listened correctly, you could answer. Okay, 6 of you didn't pay attention. Okay. So, I am saying T is in Kelvin. Okay. So, when I explained the concept of thermal stability, I said room temperature is 300 Kelvin, right. So, at room temperature or 0 degree, it is 273 Kelvin. So, you are not dividing by 0. So, infinity is not the answer. So, it should be some positive number. Okay, so we learnt about scaling. Scaling, we are reducing the thickness, we are reducing diameter, and because of scaling, we enter into the thermal stability problem because we reduce volume. So, the KVB by KVT became a problem. So, that is one thing. Okay. Second one, now we move on to the major technological jumps. Okay. So, this is another approach through which we have grown from 5 megabyte hard disk drive to 5 terabyte hard disk drives. Okay. So, to give you some example, I told you that in the old hard disk drive, RAMAC, or even in tapes, we use a particulate media. That means, we have some nanoparticles. So, these nanoparticles are embedded in some binder. Basically, it is a magnetic paint. Okay. So, if you have been to the bridge in San Francisco, right. So, that is painted with some magnetic paint. So, people used that kind of magnetic paint to make recording media, but from that scenario now we have moved to thin film media, right. So, this is one technological jump. So, we are not just spin coating disk media, we are depositing magnetic film, that is one type. Okay. So, this is the example of the magnetic paint. So, people coat the iron with this kind of magnetic paint to prevent the iron from getting corroded. So, if you read this text, right. So, when they first made the hard disk drive, they just filtered this paint using some socks kind of thing. Then they poured this paint on the spinning disk. That is how they made the recording media. Okay. That is how it was done. But from that, now we have moved on to sputtering, and the early days, the head was made with some manually wound coil, the electromagnet, but now we are using extremely high technological advanced lithography techniques to make head and so on. So previously people used Faraday's law based reed head, but now we are using magnetoresistance and so on. Okay. So from this simple spin paint kind of spin coated paint, now we have moved on to sputtering chambers with highly technological advanced concepts. Okay. So sputtering chambers have like 20 plus chambers, and they are maintained in class 10 clean room. So class 10 clean room means within a cubic meter you will only find 10 particles kind of thing, that kind of clean room. So I showed you the video. Nobody works inside the clean room. So mostly things are automated to avoid contamination, and we moved away from longitudinal magnetic recording to perpendicular magnetic recording and so on. These are all technological jumps. Okay. So whenever we face problem with some obstacle like thermal stability comes into picture, then we have to come up with some paradigm shift. So we go from what is tradition to non-tradition, break tradition. Okay. So that's what we do. That's the only way to progress. So we moved from longitudinal magnetic recording to perpendicular recording, and now we are looking at heat assisted magnetic recording. Okay, this suppose you are staying in the same company, salary is only increasing slowly, change company, then you will get a huge hike in your salary, right? Something like that. Okay, so now we move on to discuss another concept called perpendicular magnetic recording. Okay, so the story so far is with the longitudinal recording at some density we hit the ceiling. So we cannot progress further beyond that ceiling using longitudinal recording. So because of that we move to another technology called perpendicular recording technology. So we changed job, okay, we changed to new company. So in the longitudinal recording, I told you we have some underlayers. The chromium layer helps to keep the magnetization of the cobalt in plane and so on. So we have a few layers. Now it's not always one layer. We have several layers, and out of which at least one of them is a magnetic layer that stores the information. And in longitudinal, you learnt that the magnetic poles are parallel to the disk surface. Okay, in perpendicular recording, you have a magnetic layer and the magnetization is now perpendicular. So the north pole, south poles are now perpendicular to the disk surface. Pardon? Yeah, we will learn on the last day. Okay. I was supposed to discuss on day 1, but we didn't have time, so we will discuss on last day. Okay, in brief, basically overcoat prevents all the layers below from getting corroded, because you have so many metallic layers. So some of these are cobalt, some of them may have iron here. So you don't want them to get corroded. So you have a overcoat to prevent the corrosion, and then you have a lubricant layer on top, which help to prevent from the disc or head from getting damaged. Occasionally you might come into contact, right? So you are flying at 1 nanometer. Occasionally the head and disc may come into contact. So the lubricant helps to prevent the damage. So these are some polymers. So perfluoro, some polyethylene, something like that, PFPs they call. So they are helping to minimize the damage from some inadvertent collision. Roughness, no, roughness you have to manage during the deposition. So you have to start with a very smooth substrate. Then when you grow all the films, you ensure that the films don't increase the roughness. Any other question? Yeah, I'll come to that. Yes. Under layer is I mean, some layer under the magnetic material. That's why we have this name under layer. But this layer is used for increasing the C-axis structure. I told you that if you have Okay, suppose you take a substrate and you grow a cobalt film. Okay, you go to lab, put a silicon substrate in the sputtering machine, try to grow cobalt film. Then the cobalt films will usually have C axis in all random direction. Okay, so in some region the C axis will be like this, some region the C axis will be this way. So you will have very random growth. Okay, you cannot make all the C axis of cobalt grains parallel to the disk surface. Okay. On the other hand, if you grow some underlayer, I told you chromium. You remember I showed you one picture of chromium below the cobalt. So that chromium will grow with a certain texture, and when you grow the cobalt on top of that chromium, then you will have the C axis parallel to the disk surface. Okay. So we grow these layers to make the magnetization easy axis to be parallel to the substrate. Okay, so I gave you the example of a Lego block, right? So you have chromium which has certain template. On top you grow cobalt, then you will make the magnetization to be, I mean all the easy axis will be now parallel to the disk surface. So intermediate layer helps to buffer this. Okay. So sometimes what happens, the chromium may have certain lattice, let us say chromium lattice parameters 2.56. I am just throwing some number, okay, maybe this is not accurate, and let us say cobalt is 2.42, something like this. Okay, there is a mismatch. Okay. So mismatch is like you have two Lego blocks, but they are slightly the cylinders or hole, they are not matching. So you want to improve the matching, what you do, you add some more layer, okay, some intermediate layer with a lattice constant of say 2.50. Okay. So now you reduce the mismatch, then you make the cobalt grow on top of this. So that's why we have like underlayer. Underlayer makes a template, then intermediate layer improves the template. Then on top of this, if you grow the cobalt, then most of the cobalt have made C axis parallel to the disk surface. That is the idea. Okay, so you have many layers in the longitudinal recording technology. Now, when you come to the perpendicular recording technology, one difference is that the magnetization is now perpendicular, not horizontal. And the second difference, now you see that there is a soft magnetic underlayer. Okay, here the underlayer was non-magnetic. So here the only magnetic layer is here, the one that stores the information. But in perpendicular recording technology, we have a soft magnetic underlayer. Okay. So that's another difference. So the two differences are the direction of the magnetization and the presence of the soft magnetic underlayer. Okay, so I'll explain why we have a soft magnetic underlayer and why, how do we use it, I'll say in the next few minutes. Before that, I want to introduce this concept. So I have always been explaining to you the things from the writing, reading and the storing perspective. Okay, so far our story is like we have smaller grain, we need smaller grains to improve the signal to noise ratio. So the reading will be better. I mean, you can achieve high density with small grains. Okay, but the problem is when you have small grains, you have thermal stability problem. You cannot store the information reliably. Okay, so what limits us is this, right? We need to achieve KUV by KBT ratio of 60. Okay. So what we have done is we have kept on reducing the volume. Right? When you keep the KU fixed, you keep reducing the volume, you are going below 60. So you can overcome this problem by increasing the KU. Okay, suppose you have, let us say you have cobalt, chrome, platinum with an anisotropy of say 2 times 10 power 6 erg per cc. Suppose you come up with another material, let us say less chromium or something, then you increase, I mean, if that material has a larger anisotropy constant, then you can double the KUV by KBT, right. So, if you can increase the KU, you can overcome the problem. Okay. But when you increase the KU, what will happen? So, we learnt that the HK is 2 KU over MS. Okay. So, yeah, you are right. Okay. So, when you increase the KU, you increase HK, which means the saturation field will be larger. So, your head will have difficulty. So, with the 1.5 Tesla available from the head, we cannot write. Okay. So, this problem is called media trilemma. So, you have three things you have to optimize by balancing all. Okay. Dilemma is like you have a difficulty in choosing A or B. Now, you have A, B or C. You have to choose A and B, A, B and C correctly. Okay. So, you have three parameters and you have to choose all three correctly. So, this problem is called the media trilemma. Okay. So, ultimately, suppose you find some technique or method that can enable you to write information on media with high Ku. Let us say you choose some high Ku material, and if you can write on this media, then you solve the problem of thermal stability. Okay. So, you have no problem. So, ultimately writability is the issue. Okay, now it is 10:56. Should we have a break? Yeah, we will have a break, then start fresh. Okay.